Hi, good morning class. Today we're having the class in the outdoor. Before we start the class, today we will teach you about IIR filter. So in here, you can see the environment is full of the children's noise. Hi.
Hi.
Hi. So how you want to filter off those noise? So to filter off those noise, we need to learn about IIR filter to filter away this noise. Okay, so now we will start to talk about IIR filter. Okay, now we talk about the IIR filter. IIR filter is the infinity impulse response filter. So for this topic, we will learn about how to select and design the IIR filter for biomedical signal and able to design an analog IIR filter and map it into an equivalent digital filter. So for the outline of the topic, we have first is the introductions. Second is the basic IIR filter. Third is the IIR filter design by the approximation of derivative. Number 4 is the IIR filter design by the impulse invariant method. And number 5 is the design of the IIR filter using bilinear transformations. Then we will talk about the how to design the Butterworth filter, Chebyshev filter, and also the frequency conversion from analog to digital and digital to analogs. Okay, now we go to the introductions. Okay, what is filter? Filter is an electrical network that can be transmit the signal within a specific frequency of range. Okay, what is a digital filter? Ideal filter. Ideal filter would transmit the signal under the band pass that without attenuation and completely subtract the signal into the stop band, which means like this. Okay, let me draw for you. So when we have a frequency like this, okay, this one is our frequency. Okay, our frequency at the x-axis. Okay, so for example, we have a signal. Okay, this one is my voice. Okay, maybe we have another voice. Is the voice that I don't want. Okay, so in this range of the frequency, we can cut off, for example, at the frequency here is frequency 0. If, for example, the frequency more than 5 Hertz, I don't want. So I can set the frequency here and it will cut off like this. After frequency of 5, which means we have 10, 11, 12 and more, we will cut off. So this one we known as a low pass filter. And this cut off area is when the ideal filter, it will subtractly cut off without any attenuations. And here is the band pass. And another side will be the attenuation, where the signal we don't want is the stop band filter. Okay, the characteristic of the ideal filter, they have the constant gain in pass band and zero gain in the stop band. It has the linear phase response, and it must be causal and it cannot be realized. Okay, what is analog filter? Analog filter is process the analog input and generate the analog output. How about digital filter? It will process and generate the digital data. For analog, it will contrast from the active or passive electronic. For the digital, it will consist of either multiplier delay unit. Okay, how about frequency response? Okay, in the analog, we have to modify the changing of the components, and for the digital, the frequency response is change the filter coefficients. And for analog, we have using differential equation. For digital, we are using difference equations. What is differential equation? Which means we have dy over dx. Okay. For digital, we were using, for example, like y, okay, n minus 1, something like this, or yn equals to our xn, something in this format is a difference equations. So we have two types of the filter. Okay, for frequency selectivity filter, the frequency will reject the unwanted frequency from the input and allow the desired frequency. For example, you want my sound, but you don't want the sound that behind my background. So this one is to reject the unwanted frequency that the sound that at the behind of my sound. Okay. Second, the range of frequency past the filter is called as band pass, and the range of the frequency which stop the band pass we call as stop band. And the frequency that separates the band pass and the stop band is known as cut-off frequency. Okay, which means in this figure, this graph, so this is the range of the frequency we allowed to pass, and this one we known as cut-off frequency. F for cut-off. Okay, and then here is our band pass, the frequency allowed to pass through, and here is our stop band. Okay, stop band. This one is our pass band. Pass band is allowed to pass through, stop band is not allowed to pass through. And when we have the drawing like this one is known as the low pass filter. Okay, so we have a few types of the filter. We have low pass, high pass, band reject, and etc. So the most common one is this four. Okay, so you have learned this in detail. This one is our low pass, and we have high pass, which means allow the higher frequency to pass through. The diagram look like this. This one is our frequency response curve. For the low frequency, they are not allowed. For the higher frequency, then your cut-off frequency is allowed to pass through. So this side is our bands, pass band. Okay, this side is our stop band. Okay, and this is our cut-off frequency. Okay, this one is our high pass, and then we have band pass and band reject, which means the area that we allow to pass through and the area that we reject it. Okay, for example, we can set a frequency like, okay, cut-off frequency 1, for example, is 5, whatever value. Okay, and then until cut-off frequency 2, for example, is 50, or until any value that you like. This one cut-off frequency 2. So this range, we allow it to pass through. Okay, so this one is known as band pass. If this range we reject it, is band reject. Okay, like this. For example, other signal we allowed to pass through, just the cut-off frequency 1 and 2 we are not allowed to pass through. Okay, so this range we are not allowed to pass through, other, okay, we are allowed to pass through like this. Okay. Okay, so now we will straight away go to digital filter. Digital filter is a linear times invariant discrete time system. It have two types, FIR and IIR filter, which are the non-recursive and the recursive types. Okay, for the FIR filter, when we design, we will have the present output depend on our present input or previous sample. Okay, for IIR filter, we will have the present output, okay, which means present output, which means we have Y, N. Okay, this one is our present output, and this present output is depend on, which means equal to our present input X, N. Okay, and comma past input. Past input is our X, and minus 1 or minus 2 or minus any value. Minus any value that I can say is minus K. Okay. And the output sample. Output sample can be your Y, can be any value, can be your yn or yn minus 1 or yn anything. Okay, minus 1. Okay, just go like this. Okay, so this one is a IIR filter design. Okay, impulse response for the realizable filter and the stability condition must be satisfied. Okay, the filter must be satisfied. These two conditions only can be a more better filter. Okay, to design the IIR filter from the analog filter, the conversion technique should be effective if it possesses the following property. For example, J omega exists is either explained must be mapped into the unit circle of the set. We have the direct relationship between the two frequency variable in two domain. The left half plane of the S plane must be brought inside the circle of the Z plane. Okay, for example, let I draw for you. So this one is our Z plane. Okay, X plane. Okay, our X plane. Okay, so this X plane should be mapped into the unit of the circle of the Z plane. So we will have our J omega axis and our X axis. Okay, for example, we have the point at the right hand side, and this point of the right hand side, it must map into the Z plane, our Z plane, which means we have real part and imaginary. So here is our real. Okay, here is our imaginary. So for this one, this point, it must map to inside the circle of the plane. Okay, so the left half plane on the S, so which means this area. Okay, let me use other color. this green color, in this area is mapped into the Z. So it will map into here. Okay. So in the unit circle, so it's considered is a stable analog. Convert from the stable analog into a digital analog filter. Okay, clear about this? Okay. Now we go to the next one. Is about IIR filter design by the approximation of derivative. Okay, to calculate this one, we have to use this backward difference formula, which is here dy over dt. Okay, equal to these equations. So we have the equation y and t minus of y and t minus t divided by t. And now we substitute this nt, okay, as a n, because this t can be just removed. So we will have the yn minus of y n minus 1 divided by t. Okay, so now we let our yn equals to our y and t, with the t actually is our sampling interval. Okay, so in the analog system function, we will have hs equals to dy t over dt will be equal to our s. In the digital, we will have jx equals to 1 minus of z minus 1 divided by t. Okay, now I would like to prove you this s actually is equal to 1 minus of z minus 1 divided by t. So first, we use the formula from the backward differential equations. Okay, this formula 1. Okay, so we put here 1 here. Okay, number 1 here. Okay, so dy t divided by dt is, our t is equal to n t, right? So now we take this formula y n t minus of y n t minus t divided by t. Okay, okay, now we substitute our t as a n t. Okay, then after that we simplify it as yn minus of yn minus 1 divided by t. Okay, so this yn actually is 1, and then we make into z transform. Yn minus 1 is our z minus 1. Okay, then s is actually this equation, so we substitute this dy t divided by dt as s. So we put in equation 2 here, we substitute this equation here, we substitute with 2 s. Okay, and then this one we simplify it into z transform. We will get 1 minus of z minus 1 divided by t. So we get this equation. So we prove that our s is equal to 1 minus of z minus 1 divided by t. Okay, okay, when we do for second derivative is just replaced by the second backward differentiate. Okay, how we want to do this one? What we do is we differentiate dy dt. So when we differentiate dy dt, we will get du divided by dt minus of dv divided by dt over of t square. So when we do this one, so we will have this equation. You do your differentiation, right? Okay, we will get y and t minus of yn minus t for this part, and minus of y and t minus of t plus with your y and t minus of 2t. Okay, so this one is the first differentiate, this one is the second differentiate, and divided by total t. So this t we can take up, we multiply with 1 over t. Okay, we will get t square. Now we let our yn equals to be for y and t. Okay, dy over dt. So our t is equal to nt, and yn minus of 2 yn minus 1 plus with our n minus 2 divided by t square. Okay, so it's very easy. We make it into z transform again. So we will get s equals to 1 minus of 2 z minus 1, because n minus 1 is z minus 1, n minus 2 is z minus 2, and divided by t square. And this whole thing, and we can simplify it, actually is a, below is a t square, and above actually is 1 over z minus 1 if square. So which means 1 minus of z minus 1, you multiply back with 1 minus of z minus 1, you will get back this equation. Yeah, so we simplify it like this. Okay, okay, so now we know already. So when we see from here, s power of 1, we will get 1 minus of z minus 1 divided by t power of 1. Okay, when second derivative is s power of 2, okay, second derivative is x is 2, so we will have 1 minus of z minus 1 divided by t power of 2. So if I derivative, so s power of I, we will have 1 minus of z minus 1 divided by t is power of I. So we can conclude that the digital filter system hj is equals to our hj is our digital the transfer function for digital is equal to our analog transfer function HAS, and this S is equal to 1 minus of Z minus 1 divided by T. And then now we rearrange the S. So when we rearrange the S is 1 minus of Z minus 1 divided by T, and now you want to make it into a Z. So 1 minus of 1 over Z divided by T, and then this Z we bring forward to the right hand side, and our S we will bring toward to the left hand side. We will get Z equal to 1 divided by 1 minus of ST. Okay. So what is this XT? S actually is J omega. So we substitute the S, this S with J omega, we will get it minus of J omega T. Okay, so and when Z is equal to 1 divided by 1 minus of J omega T, okay, so when we square it, and to get this thing actually is we have real part and the imaginary parts. So we will have 1 divided by 1 plus omega square T square, and plus with our J omega T divided by 1 plus omega square and T square. Okay, this is just now the mapping from the right hand side. Okay, this one is our right hand side of our mapping. We will map into the circle so that our system is more stable. So the S in the right hand side in the analog. So this one is the analog plan. Okay, this one is our digital plan, Z plan. Analog plan we do as X plan, and digital plan we do as Z plan. So now we are mapping from analog into digital. So when we map analog into digital, we will get hash L. Our left hand side, the X plan is mapped inside the circle with a radius of 0.5, and the center of Z is also 0.5. So we map it into the circle. For example, we have a point at the right hand side. For example, this one. Okay, we put a color, blue color. So this point is our left hand side. If we map outside the circle, it can be moved here, for example, outside the circle. So it will not inside the circle. So it's unstable. Okay. Okay, this is just theory. Now we go to the example in the calculation. Using the backward differential for the derivative of the analog low pass filter with the system functions. Okay, for example, we have hash S equals to 1 divided by S plus 2. Okay, for this equation, how we want to do? We want to map it into the Z transform. Okay, convert into the Z transform. So now we know our S is equal to 1 minus of Z minus 1 divided by T, and then we just substitute our S. Okay, we just substitute our S equal to our this value. Okay, what we do? We put 1 divided by S is minus of Z minus 1 divided by T plus value of 2, and then we simplify it. So we simplify it, this T divide, we can multiply T to cancel off the T, so we multiply above T, so we get T here, and then here also have T, and then we cancel off this T. Okay, then after that we assume the T time is is 1 second. Okay, this one if we just assume, if the question is given, you just assume. Okay, so we will have S here. This one our time is 1, so we substitute our T with 1, this T 1, and this T value also is 1. Okay, so we will have 1 divided by 1 minus of Z minus 1 plus 2. Okay, these 2 we can sum up with our 1, so we get 3 minus of Z minus 1, 1. Okay, so it's very simple. And then after you get this transfer function, we can draw it into our realization. So how you want to draw it into the realization? For example, now we want to draw it into the direct form 2. Direct form 2 for this equation. We can just draw it into direct form 2. Okay, how you want to draw? First, we have the x input, xn, and then you equal to our, okay, first you have the multiplier is 3. Okay, then after that you sum up with your Z minus 1. Okay, so this Z minus 1 will be backward. So now this one is our negative 1. So it's 1 lah. Okay, 1. Okay, so you go straight. The above here is 1. So we put as 1. So go out your y n. Okay, this one is our direct form 2 for this equation. Okay, Then we go to the next is the backward derivative for the derivative and convert the analog filter with a system of Hs equals to 1 over s squared plus 16. So you try to do this question at home.